basically. So if you forget everything else I say tonight, the one thing to remember here is that Earth's atmosphere is always electrified. Normally, we just think about charge when there's thunderstorms and lightning around, but it's electrified all the time, and charge is continuously generated. And that's through a process called ionization. So positive and negative charge is created by ionization all the time. And in our atmosphere, there are two sources of ionization. The first is from galactic cosmic rays. So these are highly energetic particles from basically outer space, from outside our solar system, and they enter Earth's atmosphere from above. And as they do so, they create a cascade of charged particles right down to the surface. And because they come from outside our solar system, they're modulated by solar activity. So they respond to magnetic fields. The other source of ionization is radioactivity at the Earth's surface. So this is mostly from gamma radiation from the soil. And so this emits ions which can be transported upwards, but they're typically trapped in the boundary layer. So they're stuck in the lowest kilometer of the atmosphere. So this charge is being generated all the time.
Claude Shannon, the father of information theory, was deeply inspired by the close connection between entropy and information. He defined a new type of entropy, Shannon entropy. It can be interpreted as the amount of previously hidden information that can potentially be revealed by the observation of a random event. In a sense, it's a measure of the uncertainty of the event. The more uncertain or more unusual an event, the more revealing it is than a more predictable event. So for example, the roll of a die has more entropy than the flip of a coin. There are more potential outcomes in the former, so more uncertainty has been eliminated when the die is cast. Shannon used the term entropy for this measure because his formula was almost identical to the formula for thermodynamic entropy. Just multiply by the Boltzmann constant to get the latter. If you take all possible results of the die roll to be equally likely, then Shannon's formula looks just like the Boltzmann equation. This isn't a coincidence. In fact, Shannon entropy is, in a sense, just a generalization of thermodynamic entropy. Here we start to see the connection between entropy and information. If all the air is in the corner of the room, for example, then you know more about the positions of the individual particles. They're all in the corner of the room, versus if they're spread through the room. But it took the invention of information theory to really see the connection between information and entropy. It was Claude Shannon who founded the field of information theory and also invented the entropy of information, Shannon entropy. Shannon entropy can be thought of as the amount of hidden information in a system, or more precisely, the amount of information we can hope to gain by making a measurement of the system. If all the particles are bunched up in the corner, then measuring their exact positions gets you some information, but if you measure the positions when they're spread through the room, you increase your information by a lot more. Another way to think about Shannon entropy is in terms of events. The more possible outcomes of an event, the more entropy the event has. For example, a flipped coin is a low Shannon entropy event because it only has 2 outcomes, while flipping 1,000,000 coins is a high entropy event. Shannon entropy is actually more fundamental than thermodynamic entropy in that it is a generalization of the more familiar entropy. It applies to any system of information and any type of action that reveals that information. When he first came up with this theory though, Shannon didn't fully realize its importance. As the perhaps apocryphal origin story goes, he only started calling his invention entropy after talking to the great Hungarian mathematician and physicist John von Neumann. Supposedly, von Neumann said that he should call it entropy for 2 reasons. 1, it looks exactly like the equation for thermodynamic entropy, and 2, nobody knows what entropy is, so nobody would argue with him. But von Neumann probably knew perfectly well that Shannon's entropy was the real deal. 1, because von Neumann was a savant-level genius who had out-mathed and out-physicsed many of the greatest minds of the last century. And 2, because of part 1, von Neumann had already invented his own brand of entropy, von Neumann entropy. It's the entropy of quantum systems. And because everything else is made of quantum systems, it may be the most fundamental definition of entropy. Even Shannon entropy is just a special case of von Neumann entropy. At least, so says von Neumann himself. The concept of von Neumann entropy is at least incredibly powerful. It's at the heart of quantum information theory, enabling us to calculate how much quantum information is contained in a system, and it can also be used to determine how many bits of classical information we can get out of the system when we make a measurement.
Tornadoes are among the most powerful and unpredictable natural disasters, but they form under very specific atmospheric conditions. These violent rotating columns of air extend down from thunderstorms to the ground, and they're capable of producing widespread destruction in just a matter of minutes. Now, the process of tornado formation begins with colliding air masses that create instability in the atmosphere, producing thunderstorms. But crucial to tornado formation is wind shear. That's when winds blow in different directions and different speeds at different altitudes. And this creates a horizontal spinning current of air within the thunderstorm. Now, as warm air rises and cool air sinks, updrafts within the storm can tilt that horizontal rotating column of air into a vertical position. And if conditions continue to intensify, the rotation tightens and accelerates, potentially leading to the formation of a tornado.
Well, with tornado formation or tornadogenesis, what we're finding and what other people are finding is that you might have a rotational lock, but it's a rather weak rotation. And what's the characteristics of the surface are the important elements that trigger tornadogenesis. That could be topography, that could be variations in surface roughness, or it could just be surface roughness itself. And what we're finding is that circulation, weak circulation might be aloft, but what happens is the formation of a tornado occurs down in the lower several hundred meters of the atmosphere and then builds upwards. So according to that research, tornadoes don't really touch down and lift off. A better terminology would be tornadoes form down at low levels and dissipate at low levels.